Hello, my name is David Faure and I work for KDAB. In this second video of our series on debugging and profiling, I would like to tell you all about the debugging tools that exist for C and C++ applications. So you can see here the list of topics that I want to cover. I will start with automated testing. The first thing you need to do is make sure that your code is properly tested, and this in itself is not debugging, but it's what enables you to make sure that when you fix a bug, you don't introduce 3 new ones. One of the ideas that you can use for this is called test-driven development, which means writing the tests before the actual code that the test is actually testing. This way you can make sure that the test is testing the right thing. The test should fail, then you fix it, and then it passes. It's a very good idea to add full unit test coverage for classes that you are going to rewrite or refactor, so that you don't introduce regressions compared to the old code. To do this, you can use one of the existing unit test frameworks. As a Qt developer, I know especially QtTestlib, but you can also use Google Test or Catch, and there are actually many others. The goal of those is to save you time because you don't have to set up everything so that you can write a test, make sure that all the test methods are called, how to handle failures and all of that. One step further is to integrate these tests with your continuous integration so that after every commit or every night, you get a full build from scratch and a full run of all of the unit tests. So all of this makes it, it improves the quality of your application, and it is very necessary for the actual debugging that we are going to talk about, because you make sure you don't introduce regressions when actually fixing a bug. Another thing that is quite related to unit testing is code coverage. You want to make sure that you have sufficient amounts of unit tests, which doesn't mean 100%. It's usually pointless to try and go to 100%. What's important is to test the parts of the application which are critical to you. That could be simple utility classes that are used everywhere, like your string class or your vector class if you have one of those. Or it could be the parts of the application where the actual business logic is, and you don't want to have any bugs in there. So one thing you can do to find out if your unit tests are covering enough of the important code is to set up code coverage. These are tools that will tell you 90% of this file have been covered by unit tests, and you can then drill down and figure out exactly which part of the code were missing in your tests. There are many tools to do that. The most well-known is gcov on Linux. It goes together with the compilers, GCC and Clang. There are also tools on Windows as part of Visual Studio, or you can install OpenCPP coverage. Also, SquishCoco is another one. So all of these tools allow you to measure how much of your code is actually tested by your unit tests. And this is an area where there are many concurrent solutions, because it's something that is very much used in some domains. For instance, anything that will fly in a plane has to be very, very well unit tested and covered by those tests. So these are domains where code coverage is really important. Another thing that you can do to improve the quality of your code is to set up static code analysis. This is also an area with many different tools. The goal is to have bugs detecting without even running the application. Simply having some tool that looks at the code and says, here we have a construct or a pattern that looks like it might have a bug, and it's up to a developer to then look into it. Actually, these days, the most well-known tools for this are the compilers themselves. If you enable sufficient amounts of warnings in GCC and Clang or Visual Studio, you will get feedback from your compiler about what you can improve in your code. So my recommendation would be to enable as many of those warnings as you can to then detect as many problems as possible. And also use more compilers than just one. If you can use 2 or 3, that's better, because you will get different feedback from the compilers. Then there are some additional tools that you can use. For instance, at KDAB, we wrote a plugin for Clang called Clazy, which allows to detect common coding errors, especially when using Qt, but also in general C++ applications. And then there are many more specialized tools like Coverity, PVS Studio, and so many others. It's quite interesting to have a look at, for instance, what PVS Studio can find by reading their blogs, and they have lots of interesting finds in open source applications, for instance. It's quite educational. So this is also something you can set up as part of your continuous integration so that you get regular feedback on what can be improved in your code. All right, let's talk about things that look a little bit more like what you would expect in terms of debugging. The well-known debugging technique, the most well-known, would be printf, right? Some logging of message for figuring out in which function I'm going, what is the value of this variable, and so on. So there are many variants to this. Obviously, the ones that are part of C and C++, like printf and cout, or those that come with your framework, like QDebug in Qt, or Boost has something, and then there are additional libraries like log4cxx and some others that I listed here, which give you more features. For instance, it's quite interesting to be able to turn on and off whole sets of debugging statements, so that if you're debugging your parser, you would enable the parser set of messages, or if you're debugging printing, you would enable all of the messages that are about printing and so on. This is a lot more practical than having 10,000 messages per second, and then you have to filter this out, or having everything off by default and you need to come in and uncomment what you need. This is a lot easier if you can just toggle a switch somewhere and get what you need. Now let's talk about assertions. These are, at runtime, a way to say, this should never happen. If it does happen, stop the application and let me debug why it happened. So that is something you would use for logic errors. You think your program is done in a way that this can never happen. So this is especially useful for preconditions, like this pointer shouldn't be null before being passed to this function, or post conditions, like this function will never return a null pointer, or invariants, things that shouldn't change while the function is being executed. But of course, it's useful for many other things as well. You shouldn't use it for runtime errors, like this file was not found. That is not really a logic error. This is more of a setup problem. You don't want to abort your application just because the user misplaced the file. Another kind of assertions are the static assertions, where this is, again, part of compilation. The compiler will tell you this check here failed, so you have to look into it. So that is for things like this enum has the right amount of the wrong amount of values. This read-only data is inconsistent. The inheritance isn't as we expected. The architecture is wrong, and so on, like the CPU architecture. All right, let's talk about tracing. One of the things you can do is investigate which dynamic libraries are being used by your application. And that's something you would do by using tools like LDD on Linux or depends.exe on Windows, which nowadays was replaced with a tool called dependencies. And on macOS, you would use OTool. This will simply list the shared libraries that are used by your application, because possibly you're not using the one you thought, and this could be the reason for a bug. At runtime, you can also figure out what your application is doing a bit as a white box. From the outside, you ask the application, show me all the files that you're opening. That's something you can do with strace or the equivalent tools on other operating systems. You could also ask it to show you anytime it's going to read a file, open a socket, or anything that actually goes through a system call. That's what you can do with strace. It's a common debugging technique when you don't actually have the source code for an application, but it's also very useful if you do. And then we have the very well-known debuggers like GDB on Linux, which allows you to do debugging step-by-step in your application. What you might not know is that there is another debugger called RR, which allows you to go backwards and forwards in your application. Isn't that amazing? The way it works is you record the run of your application, hopefully up until a bug. And then when you reopen that recording in RR, you can go backwards and forwards and skip ahead, skip backwards, and so on. You can navigate through the run of your application any way you like. And that is extremely useful when you would usually hit that problem with GDB where you think, oh, the value is wrong. How was it calculated? And you need to go back in time. And you can't do that, right? Because you don't have a time machine. But RR has the full recording and it can go back because it has all of the information to be able to do that. So that's a very worthy tool to look into. And then, of course, there is a debugger on Windows, Visual Studio. There is debugger on macOS, and so on, right? For everything, you would find a standard debugger. It's just that RR is a bit more special because it can go back. All right. Now, for those of you doing Qt development, I want to tell you about a tool that was developed by KDAB. It's called Gamma Ray. It's actually free and open source. You will find it on GitHub. And what it can do is introspect a Qt application, which means look into it and tell you all of the Q objects that are present, all of the Q widgets, all of the QML elements in the scene, and all of the 3D elements in a Qt 3D scene, and so on and so on. So it has a large number of modules where you can get all of that information and know more about your application. It's not a debugger per se. It's not going to go step by step in your code. This is much more like getting an overview of your Qt application and everything that it has created. And it's a way to debug problems like, why is this widget not big enough? Is the minimum size wrong? Is the size policy wrong? And so on. You can get information about all of these properties from Gamma Ray. It even supports remote debugging if you're doing embedded development, and it supports attaching to a running application, which is also quite interesting. Now let me tell you about Valgrind. This is a tool that is especially known on Linux. It also works on macOS. It will run your application, though in a very slow way. It takes its time, but it will look at what your application is doing once compiled, right? It's running on the binary. And it will tell you things like, you are using memory after you deleted it. That's very bad. Or you are using this bit of memory without initializing it, and all of these kind of errors. So that's quite useful when you have behavior that doesn't seem to be reproducible. You run the application again, you get a different result. That's the type of bug where Valgrind really shines, because it will tell you exactly where this source of invalid memory use comes from. It has other tools than this one. It has Helgrind for race conditions. It has Massif for memory usage, and it has Colgrind for profiling. But for these three things, I'm going to show you alternatives that end up actually being better. But the default tool, Memcheck, is very, very useful. And finally, let's talk about sanitizers. This is another way to detect problems like the use of invalid memory or double deletion. But instead of doing that with an outside tool, what we can do with sanitizers is actually ask the compiler to inject code into your own code that does all of these verifications. Anytime your code is going to allocate memory, it will remember that. Anytime your code will use an area of memory, it will first check that it's able to do so. And this is extremely powerful. It's a lot faster than Valgrind. It is part of your compilers if you're using GCC or Clang on Linux, or if you're using Clang or Visual Studio on Windows. And you can find the actual version numbers here on the slide. And there are 4 types of sanitizers. The address sanitizer, which will tell you about all of the memory usage issues. The thread sanitizer, which is extremely good at telling you about race conditions in particular, which is something that's really hard to detect otherwise. The undefined sanitizer, which tells you about your code does some undefined behavior. And then there are some additional sanitizers being developed for things like uninitialized memory, for instance. So there we are. This was a summary of all of the debugging tools that are available for C and C++ applications. And if you want more details about any of these, we actually do full trainings on this so that you can learn more about actually using these tools, what they can do in practice, and do some exercises to get used to them. All right, in the next video, I will tell you about profiling tools. Thank you for watching.